Welcome to the basic tutorial for cryo-EM data processing through cSPARC. For this tutorial, I'll be using a subset of 20 movies from the T20S proteasome dataset. The tutorial will allow you to learn the most common job types in cSPARC's workflow, and you should be able to achieve a 3 angstrom resolution structure with this dataset. So let's get started. Once you launch cSPARC in a web browser, you are presented with a dashboard. Here, you can select your recent projects and workspaces as well as create new ones. The dash also lists the changelog from the most recent program updates as well as the most recent jobs performed. Click the project icon at the bottom of the dashboard. This will give you a thumbnail view of all the stored projects. I have obscured the details of my projects here. Click on the Add button to create a new project. Give a title to your project and a path to its directory. You can also add a brief description if you like. Once created, select the new project. The program will ask you to create a new workspace for the project. Workspaces are places where actual jobs are created. Individual workspaces are meant to separate out different portions of a project. To create a new workspace, click the New Workspace action from the right panel. Give a name to the workspace, let's call it W1. Select the newly created workspace and click the Job Builder icon on the right panel. Here, select the Import Movies job type. Provide the path to the movies directory. In this dataset, the movies are TIFF stacks. Select all the movies in the directory by giving a wildcard. Also provide the path to the gain reference file. Now provide the data acquisition parameters and hit Q and then create. The job starts importing the movies. For any job in cSPARC, you can toggle between detail and thumbnail views by hitting the cross on the top right and clicking on the job numbers. You can quickly switch between these modes by hitting the spacebar on the keyboard. This job finishes rather quickly. Then go to the Job Builder and select the Patch Motion Correction job. Connect the imported movies by dragging and dropping them to the input fields. Set the number of GPUs as appropriate to your system and queue the job. This job will correct the movie frames for beam-induced motion. While this job is running, let's create a new Patch CTF Estimation job from the Job Builder menu. As before, connect the motion-corrected micrographs and run the job with default parameters and appropriate GPUs. In cSPARC, queued jobs don't run unless the resources are available or the inputs are ready. Once the motion correction job completes, the CTF estimation job starts. While it's running, let's queue the next job, which is manual picking. Connect the micrographs from the Patch CTF job and queue it. However, as it is an interactive job type, Let's go to the Interactive tab on the top left and pick some particles. For this dataset, we will use a box size of 384 pixels. Box size is usually twice the size of the largest dimension of your particles. Use the low pass and contrast filters to better see the particles. Start picking by clicking the center of the particles. Try to pick particles having both top and side views. Deselect a picked particle by right-clicking on it. Generally, one should pick around 500 to 1000 particles to generate good quality templates for the auto-picking job. But for this tutorial, around 80 to 100 particles are enough. Click Done picking the particles once you achieve that number. The job will then extract the particle positions from the micrographs. Let's use these particles to create a template by running a 2D classification job from the Job Builder menu. Drag and drop the extracted particles to the input field. Set the number of classes to 10 and queue the job with the GPUs enabled. While the job is running and going through iterations, let's queue a selection job that would allow us to select good templates from this job. Click on the Job Builder and choose the Select 2D Classes job. Connect the particles and the class averages and queue the job. Now let's go back and speed through the 2D classification iterations. Once done, go to the selection job and choose the good classes. For this tutorial, select 2 to 3 classes with different views of the particles. Then click Done. We will now use these templates to pick more particles. Choose the Template Picker job and connect the selected class averages and micrographs from the Patch CTF job. Set the particle diameter to 190 angstroms and run the job. We will have to further curate the auto-picked particles. To do that, choose the Inspect Particles job from the Job Builder menu. Connect the particles and the micrograph inputs and queue the job. This job is also interactive. Play with the cross-correlation and power thresholds to avoid picking ice, aggregates, and carbon areas. Usually, a value of around 0.3 works well for the cross-correlation. A power threshold value between 1000 to 1700 should be good enough for this dataset. Click Done Picking to output particle locations. Now we will extract these particles from the micrographs. Choose the Extract from Micrograph job type. Connect the inputs, provide an extraction box size of 440 pixels and run the job. Now we will again classify these particles using a 2D classification job type. but this time change the number of classes to 50 and run the job. While it is running, let's also create a 2D classes selection job like before and queue it. Again, let's speed through the 2D classification iterations. Choose all the good classes from this job and avoid picking classes with neighboring particles and also classes that are Einstein from noise. Next is to make an initial model for our structure. Choose the ab initio reconstruction job from the right panel and connect the selected particles. Usually it is best to set the number of ab initio classes between 2 to 3 to further clean up the data. But for this tutorial, one class is perfectly fine. Run the job. Once you get an initial model, perform a homogeneous refinement on it to refine the structure to a higher resolution using the gold standard Fourier shell correlation. Either use the full image or use a smaller refinement box size that will speed up the calculations and run the job. Once done, you can visualize your high resolution structure in Chimera. Thank you for watching.